Time taken will give you the amount of current flowing through any given area. That is, the number of electrons passing through a given time will give you the electric current. If it was a positive charge, then it will experience a force along the electric field. But since the electron is a negative charged particle, it will experience a force in the opposite direction. Electrons are the only movable free particles or free charged particles on the surface of a conductor. Hey all, I am Hari Krishnan from the Department of Physics, Vidhyaashram PU College, the Temple of Excellence. And we were discussing about potential charges and their properties. And finally, we are going to move into a new chapter which discusses about charges when they are in motion. That is, we are going to discuss about current electricity. So let us dive into the chapter and see what current holds for us. So initially, we were dealing with charges which was actually at rest. So they were known as static electricity, that is static charges. And finally, we are going to deal with charges that are in motion here. So that is known as current electricity. So we were dealing with charges which was initially at rest. Any incident we considered a charged particle which was at rest. And now we are going to deal with what happens when those charges grow a pair of legs and run around. So what happens when the charges run around from point A to point B, and that running around, that motion of a charged particle is known as current electricity. We are upgrading from static charges which are at rest into charges which are in motion, that is current electricity. So what exactly is the definition of a current? Here in this particular case, what is the definition of electric current? So we can actually say that electric current, the flow of charges through any cross section of a conductor is steady, then the electric current is defined as the ratio of total charge flowing through the cross section of a conductor to the time taken. That is, I is equal to Q by T. Don't worry if you don't understand it suddenly, I'll just explain it in detail in a few seconds. And here we have also an equation which states that I is equal to Q by T. That is, the amount of charge flowing per second gives you the current. So that particular charge in this case is the electrons which are flowing. So we can say that the number of electrons flowing per second will give you the amount of electric current. This N is nothing but 1, 2, 3, 4, 5, 6, etc. up to infinity. That is, N is nothing but NE will give you the number of electrons, and time taken will give you the amount of current flowing through any given area. That is, the number of electrons passing through a given time will give you the electric current. Now, since we got the theory out of hand, let's look more into it and understand how exactly a conductor carries current. So, imagine that we have a wire. So, I am enlarging the wire like this. So, imagine that this is the wire piece I have. I have enlarged it so that it is a cylinder. And I have connected both ends of that particular wire to a piece of battery. That is of V volts. Now, we all know that when I connect a wire to a battery, there occurs potential difference and there occurs a flow of charges. But in this case, we are going to consider, or we are going to view this particular piece of metal wire, a conducting wire, from a different standpoint of view. So we know that there is going to be an electric field happening from positive side to the negative side, which means that the electric field will be in this particular direction. And we also know that since this is a conductor, there is a number of free electrons available for that particular conductor on its surface. So I can say that there is a number of electrons on this particular conductor. So what happens when an electron is placed in an electric field? Obviously, it is a charged particle, and when a charged particle is placed in an electric field, it experiences a force. If it was a positive charge, then it will experience a force along the electric field. But since the electron is a negative charged particle, it will experience a force in the opposite direction. So, the force experienced by this particular electron, that will be in the opposite direction of the electric field applied. So we know the equation for force, that is F is equal to QE from the first chapter. Here this particular Q is nothing but the electron, so we can write it as EE, that is the charge of an electron times the electric field's magnitude multiplied. Still, we have not discussed what actually electric current is. So, in the early stages of developing charges, Benjamin Franklin actually proposed that electric current is the flow of positive charges. He had a 50% chance of being right and being wrong, but unfortunately that 50% was in the latter and he was wrong. So he considered that positive charge flow was considered to be the flow of current. But later it was discovered that it was not the positive charges which was flowing, it was actually the free electrons which was responsible for the current flow. So we corrected it later, but out of respect for him and since all the mathematics still holds, we did not change anything regarding the flow or directional flow of current. So we can still say that current still flows from the positive end of the battery and travels through any material and reaches at the negative end. Benjamin Franklin assumed that current flows from a higher potential to a lower potential. But in actuality, since it was a flow of electrons, the current flow goes from negative to positive. But he accidentally took it from positive to negative, and we still keep that direction nowadays also, because the mathematics is still unaffected and this does not prove anything wrong, only the direction is different. So we can say that in conventional sense the current flow will be from positive to negative, and that is indicated by the letter I. So I is flowing from positive to negative, that is the conventional sense of current flow. But in actuality the electrons are flowing in the opposite direction. So current flow is in the opposite direction of the flow of electrons. So what do we call the flow of electrons? It is very easy. When the electrons are flowing from the negative end to the positive end, we can call them as electronic current. Okay. This particular I is known as conventional current, and the flow of electrons is known as electronic current. So this is how we actually define electricity or electric current. We can say that in the conventional sense, I is equal to Q divided by T. That is the definition of electric current. That is the amount of charges flowing per unit time in a given area is known as electric current. So this equation still holds. Everything Benjamin Franklin did say still holds. The only difference is that instead of a positive charge, the actual responsible factor for current flow is a negative charge, that is the electrons. So this Q is actually an E, but we can still say that I is equal to Q by T because current is the flow of charges in unit time. So the flow of charges in unit time is known as electric current. So we can relate this to a water flowing. That is, if let's say I have a pipe, and I turned it slightly so that some water flows through it, then I can say that the flow rate is comparatively low. So low amount of water is coming out of the pipe. But when I turn it completely and allow a huge amount of water droplets to come through the pipe, I can say that the flow rate is immense. So that means that by controlling the amount of water coming through the pipe, I can control the flow rate, the output. Just like that, I can say that if the number of charges coming out is low, then the current flow is also very low. And if the number of charges coming out is comparatively higher, then I can say that the flow rate is also higher. The current flow is also very high. So current and charges are directly related. If the amount of charges increase, if the amount of charge flow increases, then the amount of the magnitude of the current will also increase. And one more thing to be considered is that since force is a vector quantity, we can denote that force in vector terms. So electrons are experiencing a force in opposite direction to the electric field applied. So we know that the force applied on the electron is nothing but E times E. That is the unit value of an electron times the magnitude of electric field. So in vector sense, I can actually represent this as negative E times E. Why the negative sign is because relative to the electric field, the electron is experiencing a force in the opposite direction. So we can say that this particular force is in the opposite direction of the electric field. That is the only reason we have a negative sign here. And if you want to consider the magnitude, you don't have to take the negative sign. So that is how current flows through a conductor. So when you switch on, there is a potential difference which develops an electric field, and because of that, electrons inside the conductor experiences a force. Wherever the electrons are, they experience a force in the opposite direction of the electric field applied, which pushes them forward, and that flow results in the electric current. We can just generally say that current is the flow of charges per unit time, and that is denoted by I is equal to Q by T, and the unit of electric current is denoted by A, that is the SI unit is amperes, and or you can also write it as coulomb per second. Both are right. You can choose any of the SI units, but the general standard notation is amperes for current. Moving on, we are going to a very important topic, that is drift velocity. Drift concept is very important in your PUC standpoint of view, and it is often asked. So this is a very important topic. So this is often asked in your exams. So what exactly is drift? So you might have seen cars doing drift motions, that is in Tokyo Drift or any Fast and Furious movies. You have seen cars doing a nice turning maneuver where the car just drifts off the road. Just like that, drift in this physical term means that the electron is not moving in a linear path. Drift means whatever motion is happening here, it is not in a linear path, but rather in a zigzag pattern. That is, instead of moving in a straight line like this, the electron, the particle is actually moving in a zigzag pattern. So instead of moving in a straight line, if the path followed is a zigzag pattern, it is known as drift in this particular case. So in order to understand drift even more, I'm going to consider a conductor which is cylindrical in shape. Let's say this is my conductor which is cylindrical in shape, and it has a cross-sectional area, that is, this particular area is A. So this is A cross-sectional area, and it has a length of L. So I'm considering a piece of metal wire, let's say it's copper. So I am considering a piece of copper wire which has a cross-sectional area of A and a dimension of L, that is L length. Now what I'm going to do is connect the both ends of this copper wire material to a high voltage battery. So here I'm going to connect it to a battery so that the potential difference across this is V volts. So automatically we know that when I connect this material to a V volt battery, there is an electric field being developed, and that particular electric field is from positive to negative. And we also know that since the electric field is from positive to negative, the electrons, that is the free electrons on the surface of the conductor, will be experiencing a force in the opposite direction. So you might have the question that why is the electrons only experiencing the force? That is because in conducting materials or in conductors in general, we can say that electrons are the only movable free particles or free charged particles on the surface of a conductor, because the positively charged ions are basically embedded onto the conductor. you can know that, you might have noticed that when a particle is a positive ion, it is just the absence of electrons. So that particular ion or particular positive particle is a part of that conductor. It is basically crystallized into that particular conductor. That is why the free electrons, which are easily removable and movable on the surface, moves around and not the positive particles. Anyways, so the electron is experiencing a force in the opposite direction of the electric field that is being applied. So what exactly do you think will happen when I push an electron suddenly out of that particular surface? What do you think will happen? The electron is not alone there. That particular conductor is made up of thousands of electrons, millions of electrons, billions of electrons. So what happens when I suddenly pull or push that particular electron from that place? Imagine that it is a lower primary school. You're in second standard or third standard, and there is a bench full of kids who are crammed together and are full of energy. They are full of energy, and then what I did was I gave one more kid into that particular bench. This one is a naughty kid. So what happens when he starts pushing on one? Then immediately the kid next to it will also push the other and push the other. So it will be like a chain reaction. It will start pushing or it will start going to hit on the other person. Or much more simply, we can take the example of a bumping car. You might have seen bumping cars in Wonderla or any other fantasy parks. It is very fun to drive around in those rubber cars and just hit on the other car. So just like that, here also the electrons will randomly hit other electrons which are immediately neighbor to that particular electron. So how exactly does it happen? So the electrons will experience a force which is equal to negative E. So because of this force, the electrons will start to move. But this motion is not in a linear sense. This motion is in a random sense. They will move with a velocity, let's say, of v1. Initially, this particular electron moves with a velocity of v1 and suddenly it hits some random electron in its path. It hits a random electron in its path. Then what happens? Then due to collision, the initial electron will shift its path. So it will shift its path, let's say, to here. Just like bumping cars, we are not going to hit someone and keep going in that direction. It will be like when a collision happens, when a collision takes place, both the electrons will hit each other and split apart. And this will be in random directions. So just like how you throw marbles at each other, when the marble hits another marble, it will go in a different direction. It is not predictable. The direction of that particular deviation will be at random. Just like that, these electrons will collide onto each other and they will move in random directions with random velocities. So if initially electron 1 decided to hit electron 2 with the velocity of v1, then immediately that particular electron will move away with the velocity of v2 in a random direction. And from there, again there will be some other electron, poor electron in that place, and they will get collided and they will also move in a random direction with a velocity v3 and so on. So as you can see, the path is not linear. It is not like one electron is going, hitting on the other and hitting on the other. No, the path is very random. So one electron will hit something and it will change path, then it will change path again. So just like that, the motion is very random. That random motion is known as drift. And since we cannot predict the individual velocities like this, we cannot calculate the individual velocities of each electron, we are going to take the average velocity of this particular collision. We are going to take the average velocity of that particular collisions that is happening, and we are going to name it as drift velocity. So that exactly is drift velocity, and it is indicated by the letter Vd. So we can actually state that the drift velocity indicated by V subscript D is the average velocity of electrons in a conductor. So this is known as drift velocity indicated by Vd, the average velocity of the electrons which is going in a zigzag pattern hitting everyone and changing its direction, and this is known as drift velocity. And since it's moving at a velocity in a given conductor, we have to also consider time taking. So if imagine that this particular electron took t time to reach here and then there and then there, so it is hitting random people at random times. So let's say it's t1, t2, t3. So let's say it is t1, t2 and t3. Then again it is very difficult to calculate the individual time between all these collisions. So what we do is that again we will take the average time between collisions, that is between collisions how much time has elapsed. So after one collision took place, how much time it took for another collision. So that particular time between collisions is known as tau. So we can say tau, this is tau, is known as relaxation time. This is known as relaxation time tau, and tau is nothing but the time between collisions. So I can say that tau is nothing but the time between collisions and Vd is nothing but the average velocity of electrons in a conductor that is going on colliding with each other. So just keep those things in mind, that is Vd is nothing but the average velocity of electrons in a conductor and tau is the relaxation time or the time between collisions. Okay, tau is the time between individual collisions, the average time between collisions. Okay, so we first told that the force experienced by those electrons is given by F is equal to minus EE from the equation F is equal to QE. So this negative sign indicates that it is in the opposite direction of the electric field, and this Q is nothing but the charge of an electron. That is why we put E there. And now we also know that from Newton's laws that F is nothing but MA. So MA is equal to minus E, or in a much more simpler sense, A is equal to minus E divided by M. This M is nothing but the mass of an electron. If you want, you can put an ME here, but just remember that this A is the acceleration and this is the mass of an electron. So acceleration can be expressed in this term, and the negative sign is nothing but the opposite direction. Negative sign indicates the opposite direction of the movement of electrons. Again, we are not stopping here. Acceleration also has a definition, that is acceleration A is equal to velocity divided by time. So what exactly is the velocity here? We had discussed that the velocity inside that particular conductor is the velocity, drift velocity. So we can say that A is equal to V by T, but here V is nothing but Vd, that is the drift velocity. So A is equal to Vd and divided by not time, here the time is the relaxation time, that is the time between collisions, and that is indicated by tau. So we are going to write down tau here. So we can say that acceleration is equal to drift velocity by relaxation time. So I am going to substitute that result here. So I can write it as Vd divided by tau is equal to negative E divided by M, and this is mass of the electron. So this is the equation. From this we can calculate what is the equation for drift velocity. That is why we started the equation in the first place. So we can write Vd is equal to negative E divided by M into 2. Put it in a box. This is very important. So drift velocity is given by E divided by m into tau. And one more important factor is that the charge of an electron is constant, the mass of electron is also constant, electric field in this particular case is constant, but it can vary depending on the voltage we are using, depending on the magnitude of electric field we are considering, it can change. So we can say that the drift velocity is directly proportional to the magnitude of the electric field, and also it is directly proportional to the relaxation time. So we are going to consider the fact that here the electric field is constant. So we are just going to take the relaxation time here. So we can say that Vd is directly proportional to relaxation time. And we know that relaxation time is the time between collisions. So if drift velocity increases, the time between collisions also increases. And one more thing is that this particular quantity tau, that is the relaxation time, is inversely proportional to temperature. That is, this particular tau is inversely proportional to 1 by T, where T is the temperature. That is, if I give heat to this particular system, if I am keeping a candle under it, if I am giving heat energy to that particular system, the system gets heated up, absorbing this heat radiation, which means that the electrons will absorb this energy and will get excited and they will run around even more faster. That is, if I increase the temperature, the relaxation time will go down. That is, since these are inversely proportional, if I increase the temperature, the relaxation time will go down. That is, it will be like giving candy to a couple of 5-year-olds. That imagine that you're going into a kindergarten, already people are running here and there, and suddenly you have given them lots of candies. They will run for the sugar, they will bump on each other. That is how things happen. So they won't sit around peacefully. The time between rest and running will decrease. That is, they will rest less and run more. Just like that, the relaxation time will decrease when you increase temperature. So as the temperature increases, relaxation time decreases. So as the relaxation time decreases, drift velocity also decreases. So we can indirectly say that Vd is also inversely proportional to 1 by temperature. So these are some important things you have to remember. That is, Vd directly proportional to relaxation time tau. One more thing to be considered here is that, just an extra information is that, this drift velocity or the velocity of this electron is independent of time. We are actually considering the relaxation time here. So we can say that in a manner, drift velocity or the velocity of electrons is independent of time in this particular case. So that is one thing to be considered. Wait. We are not just done yet. We found out what is drift velocity, but we still have not come to the important point, that is the chapter name, that is current electricity. So we have to calculate current. So how do we calculate current? For that, we are going to consider a few other factors. So let's say that N is the number of electrons per unit volume. That is, in a given space, there are n number of electrons per volume. That is, we can say capital N divided by V is equal to N. So if N is the number of electron and V is the volume, we can just say that there are n number of electrons in a given volume, and that is indicated by the small letter n. So n is the number of electrons per unit volume. And we already considered the factor that L is the length of this particular conductor and A is the cross-sectional area. So we can say that the number of electrons passing through a given area in time, that is the number of electrons passing through a given area. That is, if I take this particular area and I want to know what is the number of electrons passing through that particular area, then we can say that it will be equal to Vd times A times N, that is, the Vd is nothing but the velocity or the drift velocity of electrons. So if an electron is going at a speed, let's say at Vd, then how many electrons will pass through that given area? So speed times that cross-sectional area times the number of electrons passing through that unit volume, and we have to multiply the charge of an electron, the unit charge of an electron, that is E. We can say that the number of electrons passing through this particular cross-sectional area is given by the combination of the velocity, the cross-sectional area, number of electrons per unit volume, that is how much electrons are passing through that given area with that particular velocity. So how much electrons are flowing through that particular area, and we know that the flow of charges, here it is electrons, so the flow of electrons is known as electric current. So this particular equation will give you the electric current, that is I is equal to N E A V D. So we can say that the current through that particular area is given by NEAVD, that is number of electrons per unit volume passing through a given area at velocity V, that is drift velocity Vd. So we can say that that is the amount of current flowing through that particular area of that conductor. Now we are not just done yet, because this is right, this is completely right, but we have a quantity Vd here, and for that we have found another equation. So we can write I is equal to N E A, instead of Vd we are going to write E divided by M. So E divided by mass of the electron M into relaxation time tau. So there are two E's here, so we can multiply them together and we can write it as N E square A E 2 divided by M. So this will give you the current flow of that particular region, that is Ne square by M into Ae tau will give you the current flow in that particular system. And if you want to write it in terms of current flow at per time, that is current flow in relation with time, I can just say that current flow, that is nothing but I is equal to Q by T, or we can just say that small amount of charge del Q passing through small amount of time del T. So I can just say that I del T will give you the amount of charge passing through unit time. So if you are considering charges instead of pure electrons, we can just say that in general sense that the amount of charges passing through per unit time is given by this equation. The only difference is that we have to multiply here with a del T. That is, here also we are multiplying with a del T. If you multiply with the del T, this equation can be explained in the physical significance that the amount of charges passing through unit time is given by this particular equation. If you do not add the del T, then it will be just the current flow in that particular region. If you add del T, the amount of charges flowing through that particular region in unit time, that is the only difference. So we can just write I is also equal to N E square A divided by mass of the electron N E into tau times E. So this will give you the current flowing through that particular conductor. If you multiply that by del T, it will give you the amount of charges flowing through that particular area in unit time. That is the difference. So these are two important equations you have to remember, And we are just not done yet. Also, we have just one more thing to calculate. Now we are going to express all these terms in terms of current density. That is, we saw what was charge density, that was charges given per unit area, that was denoted by sigma. Similarly, we are going to consider current density indicated by the letter J. So we can say that J is equal to current passing through unit area. What is the amount of charges flowing through unit area? What is the amount of current flowing through that particular unit area? That is given by current density J, which is given by I divided by A. Or we can just say that J into A is equal to I. So we know that current density times cross-sectional area will give you current flow. So we are going to substitute, instead of I, we are going to substitute JA. So we can write this as JA, that is equal to I, which is equal to NE square A and E square A divided by mass of the electron times E times 2. So there is an A, we can cancel them out, and we can see that the cross-sectional areas cancel each other out, and we can say current density J is equal to NE square E2 divided by ME. So this is the equation for current density of that particular conducting material. And the small thing or the small nuance here to notice is that these particular quantities, that is N E square by M tau, all these quantities except for the electric field, that is applied into the conductor, all other factors depend only on the material used to make the conductor. That is, depending on if it is silver, copper, iron, gold, or whatever it is, these factors depend on the substance used for the material. And the electric field is the only part that is not depending on the substance of the material. So we can say that this particular quantity, that is J is equal to NE square 2 divided by ME E. So this particular quantity, this quantity is known as sigma, that is conductivity of a material, not charge density. It is a different thing. We use the same symbols for many things. It is quite complicated, but still. Here in current electricity, sigma denotes conductivity, that is how easily a material can conduct electricity. So this is known as conductivity. So this particular sigma is known as conductivity of that particular material, and that depends on the electronic configuration, relaxation time and mass of the electron, and not on the electric field. So this particular quantity can be written as J is equal to sigma times E. This is one more relation for current density. So J is nothing but current density, and this is one more way of expressing that. That is, current density is conductivity times the electric field, the magnitude of electric field times conductivity of a material. How easily that material can conduct electricity is known as conductivity of that particular material. You only have to remember up to this part, whatever I'm going to say right now is extra information. So we're going to jump into the topic Ohm's law in a very short while. So just before that, I want you to understand where the derivation or where the Ohm's law concept came into place. So I am going to substitute, that is JE, that is current density, into this particular equation. We have NE square A by ME, that is NE square tau by ME, NE square tau by ME here. So I can write I is equal to sigma AE. I can write that sigma AE because this particular quantity, that is NE square M2, is nothing but conductivity. So I'm going to write sigma AE. Okay, is that clear? And from the previous relations, I know that E is equal to V by D, that is potential by distance between them. In this particular case, the distance is L, so I can write V by L, or EL is equal to V. From this particular relation, I am going to write, instead of E, I am going to write V by L. So I can write it as sigma A V by L. And I am going to group together all these quantities. All these quantities I am going to group together, and I am going to write I is equal to sigma A divided by L into V. I is equal to sigma A by L into V, or I into L divided by sigma A equal to V. This particular equation, if I keep this particular quantity as a constant, then I can say that I directly proportional to V. So this relation is nothing but the Ohm's law concept. That is, this is nothing but Ohm's law. I don't want you to have any doubt from where Ohm's law concept came into existence. That is why I'm showing you this. So this particular quantity L divided by sigma A, that is inverse of conductivity times area and length on the numerator, will give you the resistance. That is, this is nothing but I R is equal to V. So this is the relation, or V by I is equal to R. That is the relation between Ohm's law, and the law states that current is directly proportional to the voltage applied across two ends of a conductor. So this is how we get Ohm's law. But the only thing you have to remember right now is up to the point where I explained current density and conductivity. So remember, up to that point, that is enough for now, and we are going to dive deep into these concepts very soon. And finally, the last topic of this class, that is mobility. Mobility means how easily a charge carrier can move. That is, if I have a conductor, let's say like this, then how easily can a charge carrier, for example an electron, a proton, or whatever it is, charge carrier, let's say in this case it is an electron, how easily it can move through that particular medium or that particular conductor is known as mobility, given that the electric field is applied. So when an electric field is applied across a conductor, let's say this is the electric field applied, how easily can a charged particle, a charge carrier, that is in this case an electron, how easily can it move in that particular conductor is known as mobility, and mobility is indicated or represented by the letter mu. So mu is mobility, how easily a charge carrying particle can move in a conductor when an electric field is applied. And the equation to find mobility is mu is equal to drift velocity divided by the electric field. So Vd by E. So we know what Vd is actually equal to. It is equal to E by m into 2. I'm only considering the magnitude here, that is why I did not put a negative sign. If you want, you can put it, it's completely fine. Divided by the electric field. So E and E will get cancelled, and finally we are left with the equation, that is E2 divided by ME. So we can write mu is equal to E2 divided by ME. So this is the equation for mobility of a charge carrying particle in an electric field. And we can also say that Since E and ME are constants, we can say that mu is also directly proportional to relaxation time 2. So that is mu is directly proportional to 2, which means that 2 was inversely proportional to the temperature. So 2 was inversely proportional to the temperature. We can say that mu is also inversely proportional to the temperature. That is, if I increase the temperature here, the mobility will get affected. How? Inversely. If I increase the temperature, mobility will decrease. How easily can it move? Because when the temperature is increased, the heat energy is given to that system, heat energy is absorbed, the electrons get vibrated, it gets all fussy, and it becomes very difficult for that electrons to freely move about that particular conducting material. So we can say that mobility is directly proportional to relaxation time and mobility is inversely proportional to temperature. So the factor affecting everywhere here is temperature. Temperature is an important quantity affecting many things. So in most cases, we'll be keeping temperature constant. This was all about a quick dive into a new chapter, that is current electricity. How was the chapter? Very shocking, right? So yeah, I'm going to deal with new topics in the next class. Until then, I hope you have understood what is drift velocity, mobility, and certain terms related to that. In the next class, we will be seeing about Ohm's law. So until that, I hope you have a great day. Thank you.